code. Okay. So, so now as I told you, tutorial 2 and tutorial 3 is regarding with error correction, actually, error correction. Okay. So if we consider the error control, okay, if we consider the error control, we can say there are two types actually. We can do error detection. Okay, the one is error detection, one way is error detection, and one other way is error correction. Okay, and I think you know some error detection methods. Okay, CRC, cyclic redundancy check, parity check. Okay, so these are error detection methods. Okay, so sometimes we use error detection. Okay, and if we detect the error, we can sometimes we ask receiver, we ask transmitter to resend it. Okay, and sometime for selecting purpose also error detection are used. Okay, for example, if you transmit a signal, okay, if you get the signal by two antenna, okay, two antenna, and you can perform the CRC for each antenna, and the lowest error detected signal you can choose as the signal, okay, as the processing signal. Okay, sometime in if you are in industrial training, if you are in the industrial training, this method is used in mobile networks equipment. No, this two antenna is for diversity. This is we call diversity reception. Okay, so sometimes we use this error correction also, error detection also there. Okay, and when we talk error correction, okay, that means this is also called as forward error correction, no, FEC. That means here we are detecting and try to correct the error itself. Okay, and we don't ask we don't request sender to resend the signal. Okay, so this is we use to save the latency time, propagation time, etc. No? So I hope you can understand, and maybe in theoretical class you have seen them. Okay, so if you use error correction, okay, we can say there are two types. Okay, one is block codes, other is convolution code. Okay, so this block codes and the Hamming codes are Hamming code is come under is coming under this block codes. Okay, and convolution codes, and the convolution code we have we can we have binary convolution code. Actually, now we are going to do some exercise in this case. Okay, binary convolution codes. Okay, so it is just a recap. Okay, so we will go to our tutorial. It is tutorial 3, and you can see that the answers are there with you with the sheet. Okay, so you can see that to find the output sequence here it used polynomials techniques. Okay, but I think it is better to use that table method. Okay, because you can draw the state diagram and trellis diagram using that table. Okay, So I think it is better to go through that table method. It is appropriate to go through that table methods. Okay. So we will find, we will go through it. Okay. Is it okay for you? Otherwise, from this polynomial, I don't know how to, actually, I don't know how to draw the trellis diagram. Okay. To draw the trellis diagram, I need that table. Okay. So what is your opinion? We will use the table method, no, rather using this polynomial method. I think table method is somewhat easy. Okay. So what is the recommended procedure you have learned in your theoretical class, with your theory class, with Dilanka method? Okay, table method. Yes, thank you. So we will go through that table methods. So here I will do this first question, and also this is the sixth question. Okay, I hope this is the sixth question in tutorial 2, tutorial 1. Okay, and I will do this one. Okay, if we have time, we will try to do this one also, because this is 2 input 3 output case. Okay, so this will not come to your exam. Okay, so 2 input 3 outputs case will not come to your exam. I check it with Dilanka madam. Okay, so this will not come to. You will get 1 input 2 output case most probably, and sometime 1 input 3 output case. I think that is simple. Okay, uh, that that type of questions are simple. Okay, anyway, if we have times, we will try to do, we will not try to do this completely, we will try at some level. Okay, so yeah, I will explain. Okay, actually constraint length means nothing but it is the number of flip-flops. Okay, constraint length means number of flip-flops. Okay, so I will now you may think that here only one flip-flops, and why it is k is 2. Okay, I will explain. Okay, so I will get this question. Okay, so if I get question, so how can I get it? Give me a few moment. Okay, so this is the question. So can you see the question? Okay, I hope you can see the question. Okay, okay, so we will continue. Okay, so so when we are learning the convolution code, okay, actually this is binary convolution code. So okay, this is binary convolution code. Okay, so there are some parameters, important parameters. Okay, the one is number of input at one time. Okay, number of input, normally denoted by n, simple n. Okay, and number of output, normally denoted by simple k. Okay, and so sometime there is another parameters called rate, and rate is defined as number of input divided by number of output. So this is the rate of the convolution code. Okay, convoluter. Okay, so this is the rate. Okay, so in this case, the input is 1, number of input is 1, and there are 2 outputs. This is output 1 and this may be output 2. So there are two outputs. Let's say that x1 and x2. So there are two outputs. Okay, so number of input is 1, number of output is 2. So rate will be half. Okay, rate will be half, and it is given. Okay, and there is another parameters called constraint length. Constraint length. Okay, so you can see that actually there may be other explanation also for constraint length. Okay, so I hope it is better to search the Google. Okay, but this convolution length is directly related with the number of flip-flops or number of memory location. Number of memory location. Okay. Okay. So I think for your exam, this knowledge is enough, but you want much definition, higher explanation, you can please search the internet. Okay. So so here the constraint length means number of memory location or number of flip-flops. Okay, so you can see that we can implement a convolution coder. Okay, convolution encoder using a logic gates, no logic circuit, logic gates, basic logic gates. We can implement this convoluter. Okay, and you know that normally for memory, if you want to get some bits in a memory, you can use flip-flops. Okay, so here there is one flip-flops. Okay, there is one flip-flops. Okay, but for this input also there should be another flip-flops. Okay, for this input also there should be another flip-flops. So all these circuit will be a convolution encoder. Okay, so there are two flip-flops actually, one for input and others are mentioned, and these flip-flops will define the number of states. No, can you remember number of states? Number of states. Okay, so if you can't any flip-flops, if you can't see any flip-flops here, there are already one for input. Okay, so there are two flip-flops. Okay, so that is why constraint length, this is normally denoted by capital K, is 2. Okay, so here the number, the constraint length is also given, it is 2, and we have one flip-flops here to define the state and another flip-flops for input. Okay, so we will go to the question. Okay, and it is said that the binary code is given like this. Okay, and you can see some dot here. Okay, dot here, that means the signal is coming from this side. No, this side from here. Okay, so these are the future bits. Okay, that is why it's put some dots. Okay, so this will be our first bit, this is second bit, third, fourth, fifth, so on. Okay, so this is come in this direction. Okay. Okay, so you can see here only one flip-flops inside. Okay, so you normally we can denote these flip-flops using M. Okay, so one flip-flops I denote it using M. Okay, and input I denote it as I. Okay, so you have M and I. Okay, so this is the M value and this is the I value. Okay, so you know that this M can be 0 or 1. Okay, this M can be 0 or 1. Okay, so this two bits will define the number of state. Okay, so there are one flip-flops. Okay, only one flip-flops. So how many status we can define using this one flip-flop, using this M flip-flops? How many status can we define? Can anyone feedback, please? Please, someone feedback. Can someone feedback? How many status we can define using one flip-flops? It should be 2. Yes, thank you. It should be 2 because only 2 bits we can have. Okay. If there are two flip-flops for other than the input flip-flops, if there are two flip-flops, we can define 4 status, no? 0, 0, C1, 0, 1, 1, 0, 1, 1, so on. Okay. If we have 3 flip-flops other than the input flip-flops, we can define 8 stages. 8 status. Okay. So here only we have 1 flip-flops. Okay. So we can only define 2 status. Okay. 0 and 1. Okay. So let's say this 0 status is A and the 1 status is B. Let's say, okay. So this is the current status. Okay. If the M is 0, the current state is A. If the 0 is 1, the current state is B. The status is B. Okay. And you know that this current state can be 0 when this input is 1, 0 and 1. No, with the 0 and 1, if these flip-flops have 0, this input flip-flops have 0, and this can be also 0. And if this has 1, this can be also, here also there is 0 itself again. Okay. So this M can be, so this input for input 0 and 1, the status, the A status can be there, no? The status, if say this is the first status, for these 2 cases, for this first status is there. Okay. And in same way, the second status, if the second status is there, that means if 1 is there, that 1 can be there. Okay. 1 can be there if this input is again 0 and 1. Okay. So altogether we will have 4 combination with the input. Okay. So with the input there are 2 bits actually. So we will have 4 combination like this. Okay. So this is input. This is your status. Okay. And here I mentioned the current status. Okay, like this. Okay. And so you can see that if 1 bit is given here, if 1 bit is given here, some process will I will clean all these. Okay. Please try to understand this. Once you understand this, I hope you can do any question. Okay. So it is easy to explain within this phenomena. That is why I am going to explain it. Okay. So next question we will just carry on. Okay. But this time we will spend some time here to get the understanding, to get to have a recap. Okay. So you can see that if you give a bit, so here the first bit is 1. If you give 1 here, okay, so there may be any process. There any process can be happen here. Okay. Then you can see that after the processing, it gives 1 input, x1, and also it gives another inputs, x2. There are 2 inputs. So you can see that this one code, 1 bit is converted to 2 bits. No, this 1 bit is converted to 2 bits. Am I right? Okay. So actually that is the convolution codes. Okay. So we are adding a bit for error correction method. So that is why for 1 bits there are 2 bits. 1 bits for error correction. Okay. Error detection and correction. Okay. So you can see that here you have also 2 input, 2 output, x1 and x2 also here. Okay, x1 and x2 also here. Okay, so I will write the output here, x1, x2, and this is our status. The status is 0, 0 and 1, 1, correct? 0, 0 and 1, 1. Okay, and the current status I denoted using A. So here AA and here BB. Okay. Okay. So we will see what happened if the input is given. Okay. Okay. So what happened if the input is given? Okay. So you can see that. So at the initiate, okay, at the initiate, the input flip-flops have 0 and this flip-flops also have 0. Okay, and you can see that the x1 is given by, so you can see that this flip-flops is directly connected to XOR gate, no? And output of this flip-flops also connected to a XOR gate. Okay, so x1 will be what? Our input XOR and the value of this flip-flops, no? Okay. And x2 will be, x2 directly we get using any XOR or other device, we directly get here. So x2 will be I input. So we get the direct, we get input bit directly to x2 as x2. Okay, as another bit, correct? So this is x1 and x2. Okay. So say that you can see that. So here the input is 0 and flip-flops is 0. Okay, flip-flops is 0 also. Okay, and flip-flops is 0 means it is in A condition. It is in A status. So current status will be A. Okay. I'm sorry. Here no need to put them. Okay, because we put them already here. Okay, and here we know the current state here for this column. Okay. So this will be A, this will be A, this will be B, this will be B status. Okay. So you can see that if input is 0 and the flip-flops is 0. Okay. So another thing is, so this M, okay, this M value of this M is defined the current status. Okay. This value of M is defined the current status. Okay. So that is I mentioned earlier. Okay. At the beginning I have mentioned. Okay. So now what bit is coming here? Okay, let's say it is the 1 is coming here. Okay, so 1 is coming here. So here also there is a clock pulse actually. Okay, so this circuit is working according to the clock. Okay, so whatever the bits, whatever the value it keeps until this clock period. Okay, so this is one clock period. Okay, when it maybe sometime this. Okay, this may be the clock period. Okay, okay, up to this. Okay, this may be a clock period. So then after other clock, that means when it comes to this period, so this change, that bit is sent here. Okay, after that clock pulse, the bit is sent here. So this will be other clock period. Okay, and this will be another clock period likewise. Okay, so I hope you know this. Okay, so I'm not going to explain it too much. Okay, so anyway, I want to tell you is that this circuit is operated under a clock pulse. Okay, clock pulse train. Okay, this circuit is operated under a clock pulse train. Okay, so every change happen within after one clock cycle. Okay, so say that next clock we get one here. Okay, so these flip-flops are memory locations. Okay, flip-flops are memory location. So at the beginning, input flip-flops have 0, and also this M has 0. Okay, then we push 1 here. Okay, we push 1 here, then this will replace to 1. Okay, and what happened to this 0? It will push to other flip-flops for these flip-flops, and again the that flip-flops value will be 0. Understood? Okay, so if we give the 1, okay, if we give the 1, okay, and the M, the value of flip-flops will be again 0. Okay, okay, so and it is our second step. So this is our first clock cycle, and this is our second clock cycle. Okay, and if we send other bits, it may be our third, fourth, so on. Okay, so I hope you get the idea. Okay, now we will try to fill this table. Okay, to fill this table. Okay, so you can see that say if I put again another bit here. Okay, so now this flip-flops has 1. Okay, now that 1 is, if we put another pulse, if you push another bit here with another clock time, this flip-flops will replace with that bits. Okay, and this the existing bits will move to this M flip-flops. Okay, can you understand? So whatever the value in the input flip-flops, okay, input flip-flops will move to the status flip-flops. Okay, so so the status is changed according to the input bits. No, this flip-flops value, this M flip-flops, this is M flip-flops, that value will change according to the input. Okay, okay, so this input also define the next status level. No? Okay, so whatever the value in this input, okay, after next clock cycle, that will be moved to the M, that will be moved to this M flip-flops. So this will define the next this will define the next status. Correct? Okay, so these are the things you should understand when you fill in this table. Okay, I hope you get it. Okay, so we will try to fill this. Okay, and you can see that this x1 we can get by XORing input and the the value in M flip-flops. That means I XOR M, and x2 is directly input. Okay, so if we have input as 0 and the M flip-flop 0, okay, so what will be the output? X1 will be I XOR M. So 0 XOR 0, you will get 0 again. Okay, and x2, as x2, you will get 0 itself, no, directly 0, because x2 is directly equal to I. Okay, so you will get x2 as 0. Okay, so you can see that if we define the next state, okay, if we define the next state, it will be the value of this I, no? Okay, so this next state will define the value of this I. Now value of this I is 0. So next state will be 0 again. So we denote 0 state as A, no? So it will be A. Okay, so say that the input flip-flops is given 1 in next cycle. Okay, and still the M, the status of this M will be 0. Okay, will be 0. And so status 0 status we denoted as A. So current status is A, and this input will define the next status. So this next status will be status 1. That is we denoted as B, no? So next states will be. Am I disconnected? I couldn't notice it. Again, I reconnected. I hope I have disconnected at some time. Okay. So I think it is not for much longer, no? So we can continue. Okay. I hope you will not miss any information. Actually, these are maybe you are boring with this information. Is still if you know these things, okay, but I explain it, some student may not be familiar, okay. That is why I explain this first question in this level, okay. So in the next clock cycle, you will have input as 1 and the bit in M is 0. So you have to find the X1 output 1, you have to XOR this one and this bit, okay. So if I XOR 1 and 0, I will get 1, okay, and X2 I will get directly 1, okay. In same way, you can do other, you can fill the other row also. Here it is 0 and 1. So X1 will be 0 XOR 1 and you will get 1 again, okay. And X2 will be 0 because I is 0. So it is directly get as, it is directly taken as I. Sorry, it is directly taken as X2. So it will be 0, okay. And you can see that now the input is 0. So next status will be 0 status, that is B, status A, sorry, status A, no? 0 status we denote as A. So it will be A again, okay. So here also you can put the value, okay, like this, okay, for your table. But probably in most you can see in most cases we put some English letter, simple English letter to denote the status. That is to reduce the confusion, okay. Otherwise, sometimes these bits are confused with these bits, okay. So that is why it puts some English letter to denote this status, okay. So this is A, and you can see that now input is 1. So next status will be B because it is 1, okay. And you can see that here 1 1 you have. So if I 1 XOR with 1, you will get 0. So this is modular 2 arithmetics. You know the XOR operation. So 1 1 you will get 0, okay. And X2 you will get directly 1, okay. So this is the table, okay. This is the we can say that this is the state table or something. No, I can't remember the table name, okay. Okay, let's say this is the state table, okay. So we have found our state table like this, okay. So actually using this status, using this table, you can find the encoded bit, okay. You can using this table you can get the encoded bits, okay, encoded bits, okay. And if you draw the code tree, also you can find the encoded bits, okay. And if you draw the trellis diagram, okay, trellis diagram, and in that case also you can find the encoded bit, okay. So this is the transmitting, okay. And if you send this, you will receive somewhere. Okay, then you have to decode this. To decode this, you have to use the trellis diagram again. Trellis diagram. Okay, using trellis diagram, we decode it, and decoding algorithm we code as Viterbi algorithm. No, Viterbi algorithm. Okay, so you should be able to encode any bits. Okay, encode any bits and decode it using the Viterbi algorithm. That is the things you should be able to do. Okay, so you can see that this trellis diagrams, we need trellis diagrams to decode the signal anyway, and using the trellis diagram also we can encode the signal. So drawing this trellis diagram is also very important. So I think you should be able to draw the trellis diagram correctly. Okay, so we will try to draw the trellis diagram for this one. Okay, to draw the trellis diagram, I think you already know that. Okay, we have to, okay, we have to put our status. So there are two status, no? So I denote it as A and B. Okay, so this is my two status. Okay, so after one cycle, after one clock cycle, okay, after one clock cycle, this status can be changed, no? So it can be changed to A or again to B. Okay, and after another clock pulse, again that status can be changed. After another clock pulse, this status can be changed. Okay, like this. Okay, so if we consider the first clock pulse, okay, so at the beginning, the status should be at A because m is equal to 0. Okay, and I think the one thing you should get remembering, that is, for 0 input we use thick lines, no, and for 1 input we use dash line. Okay, and you can use two colors also. For 0 you can use red color, and once input once you can use blue color or something. Okay, likewise you can use two colors. Okay, and I will use thick line and dot line. For thick line for 0 input, and dotted line for 1 input. Okay, input 1 for input 1. Okay, for this is for input 0 and this is for input 1. Okay, so now I am in status A. Okay, I am in status A. If I have 0 input, okay, if I have 0 input, okay, if I have 0 input, okay, 0 input, again I will be moved to the A, no, again I will be moved to the status A. So if I have 0 input, I will move to, sorry, 0 input, I will move to A status. Okay, so if it is 0 input, so I use thick line. Okay, and when I move to this A to A with the 0 input, what is the output? Output will be one bit is 0 and one bit is 0. This is the output bit, x1 and x2. So I get x1 as the first bit and x2 as the second bit. Okay, you can change this. Okay, you can change this, no issue. If you change this, you will get another code wise. Okay, but in normal way, we can assign x1 as first bit and x2 as 0 bits. Okay, so I hope you get it. Okay, So here A to A. Okay. So the output I have to put in above this line or somewhere. Okay. So output is 0, 0. Okay. Output is 0, 0. So this is the output. Okay. Now I am in status A. Okay. So at first cycle, there will not be a status B, no? Okay. There will not be a status B at first cycle. Okay. But after second cycle, another thing is, if you have one state input one, okay, input one, okay, you will move to the status B. Okay, you will move to next status as status B. So if you have one, so if we have one input one, we have to denote it, represent it using dash line, no? Okay, so I denote it using dash line. So here input one, and if I given if input one, the status will be B, next status will be B, and what is the output? Output will be 1, 1. Okay, so output will be 1, 1. Okay, and so this is the first cycle, first clock cycle. Okay, this is the first clock cycle. Okay. So we can have two options. Okay, at first clock cycle, we will have two option. Okay, if it is 0 and if it is 1, if the input is 0 and if it is 1, if the input is 1, so we will have these two cases. Okay, and when we go to the second clock cycle, now if you are in A, okay, if you are in A, if the input is 0, you will move to the status A again and output will be 0, 0. And if the input is 1, you will move to the state B. Okay, and the output will be 1, 1. Okay, and also you can this will continue to all other clock cycle. Okay, this will continue to all other clock cycle. Okay, and here from second clock cycle we will have another option. Okay, sometime we may in status B. Okay, so if we in status B and if we get 0 input, we will move to, if we in state B, okay, this is state B, and if we get 0 input, we will move to the A. No, we will move to A status. Okay, so if we are in B and if we have 0 input, okay, if we have 0 input, that means we have to represent it using thick line. If we have 0 input, you will have you will move to status A. And what is the output? Output will be 1, 0. Okay, so output will be 1, 0. No, these are the output 1, 0. So output will be 1, 0. Correct? And you can see that if B and if there is B and input is 1 and it is again at status B, no, B will go to the status B again. So it will go to status B like this. Okay, so this is, so what is the output? Output will be 0, 1. Okay, output will be 0, 1. Okay, and this is all for other clock cycle also like this. So this is the trellis diagram. Okay, likewise we can draw the trellis diagram. Okay, so so now the bit stream is given, no? 1 0 1 1 C 1 0 1 1 1. So this 1 is given in first cycle, this 0 is given in second cycle, and 1 1 1 is given in other cycles. No, okay. So our input will be in first cycle it is 1, second cycle it is 0, okay, 0, and third cycle it is 1, fourth cycle it is 1, and the next cycle also it is 1. Okay, so you can see that now we are in state A and input is 1. Okay, so this input is 1. This is the input, no? So we have to go through this dash line. So what is the output? Output will be 1, 1. So instead of this 1, input 1, so this is our input. Okay, and our output will be 1, 1. Okay, and see the next. Now the status is in B. Okay, so we are in B. Okay, now what is the input? Input is, what is the input? 1 0 1 1 1. Oh yeah, yeah, write it 1 0 1 1 1 1 0 1 1 1, so on. Okay, so here it is, if the input is 1, it is 1 1. Okay, now input is 0. Now we are at state B. Now we get 0 input. 0 input we denote it thick line, no? Sorry, yes, thick line. So this is our output, no? With this thick line, we will get our output. So this is our output, 1 0. Okay. Okay, and we are now at the status A again. Okay, so we are at the status A and we get another 1 input. 1 input means we have to go through this dash line. Okay, so what is this value? It will be 1 1, no? Okay, so for this, and again we are changing to B. Okay, status B, and now output will be 1 1. Correct? Okay, output will be 1 1. Okay, and now we are in status B. Now we are in status B. Okay, now we are in, at that time we have 3 clock pulse. Now we are in 4th clock pulse, in this clock pulse. Okay, so now we get again 1. Okay, we get again 1. Yeah, we get again 1. Okay, so what happened? The input is 1, so we have to follow this dash line. Okay, that means again it come to B, no? It is come to state B. So what is the output? This one will be 0 1, no? This one will be 0 1. So I will get here 0 1. Okay, and in the next cycle also we are in status B and we have 1 input. So that will also will be 1 0 1. Okay, that will also will be 0 1 0 1, like this, so on. Okay, so we can encode this like this using the trellis diagram. Okay, did you get this? Okay, if you can't get this, please go through this lecture again, session again, and try to understand. If you still can't understand, please ask me, then I can help you again. Okay, so if I going to retell it, okay, maybe it is not, you will be confused and it is wasting of time. We are now quickly running out of time. Okay, so and also you have many YouTube's video on this. Okay, I think that's explanation may be clear than my one. Okay, and I hope you can follow that lecture also, that YouTube lectures also. There are some professors and doctors are doing very clearly, so you can follow that one also. Okay, if you can't understand this, but I think it is very important to understand this process. Okay, because you have to do this in your exam. Okay, and also when you are doing final year project, okay, and I don't know, maybe now you are doing final year project. Okay, you can choose this kind of project. Okay, uh, implement convolution code, implement Hamming code. Likewise, you can do this kind of project also. Okay, so this is very important. So please try to get the understanding. Okay, okay, so this is how we encode. Okay, and how we decode the system. Can you remember? how we decode the system signal. Okay, so I know this. Okay, and for decoding, that means now this is our this is now we have this input. This is our information. Okay, this is our information. We have 1, 2, 3, 4, 5 bits. Okay, so instead of 5 bits, now we have 10 bits. Okay, now we have 10 bits, and this is ready for transmitting. No, now we have added the error correction codes. Okay, we have added the error correction codes. Okay, now we have 10 bits to transmit. Okay, now you can transmit this bit using any modulation techniques. You can transmit. Okay, so to transmit this bit, you have to convert this to, if you want to transmit it wireless, you have to modulate it. If you want to transmit this by a cable, you no need to modulate. You can use a line coder and convert these bits into a voltage, and you can just send. Okay, so at the so this is the transmitter. So we are doing the we have done the job at the transmitter. Okay, and what if this received at receiver? We have to decode this. No, we have to decode this. Okay, so this 10111 we have converted to source code. This is called as encoding. No, encoding. Okay, so we have encoded signal here, 10 bits. Okay, so we have 10 bits here, and we have to decode this to again 5 bits. No, that 5 bits. Okay, so to do this process, to do this decoding process, you are using Viterbi algorithm. Viterbi algorithm. Okay. Okay, so we will use the Viterbi algorithm also here. Okay, we will try to recap. Okay, so Viterbi algorithm, in Viterbi algorithm, what you are doing is you take the input bits. Okay, you take the input bits. So this is the first cycle. Okay, this is the second cycle bits, and this is the third cycle, fourth cycle, fifth cycle, so on. Okay, so this is the first cycle bit. Okay, so you take the first cycle bit. Okay, and this is the second cycle bit, and you can see that this is our second clock cycle, and the bit is this one, and this will be 0, 1 and 0, 1. Okay, so this will be our received signal, received symbol, received bit. Okay, this will be our received information. Okay, received information, and it will be 1, 1, 1, 0, 0, 1, 0, 1. Okay, so now you have to, in Viterbi algorithm, what you are doing, you are finding the Hamming distance between these outputs. Okay, then you put it here. The Hamming weight, you put it here. Okay, by calculating all the Hamming weight, you put here. And the minimum Hamming weight path you will consider to decode the signal. Okay, so I will explain it by doing this. Okay, so that is the process. Okay, so first thing is to calculate the Hamming distance. Okay, so how to calculate Hamming distance? So here 1, 1, this is our input bits. Now input bit means input to decoder. Okay, this is input to decoder. Okay, but this input bit is input to encoder. Okay, so in this case also I mentioned this as input. Okay, so don't get confused. This is the input for decoder. Okay, so here 1, 1, and you can see that there 0, 0 is there. So Hamming distance is 1, 0. To calculate the Hamming distance, we get the if the bits are same, there is no Hamming distance 0. If bits are different, the Hamming distance is 1. No? So Hamming distance also calculate using the XOR gate actually. Using the XOR gate, you can calculate XNOR gate, no? Maybe please check, okay? XOR or XNOR gate, you can calculate the Hamming distance very easily, okay? So here, 1, 0, okay, 1, 0, so Hamming distance is 1, and here 1, 0, another Hamming distance. So the total Hamming distance is 2 here, okay? 2 here. And in this case, 1, 1, here 1, 1, so 2 bits are same, so here the Hamming distance is 0, okay? So here the Hamming distance is 0. And if you consider this one, so you can see that 1, 0, 0, 0. So one Hamming distance, no? So there are one Hamming distance. So if you consider this part, this 2 plus 1, so here you will get 3, okay? And if you consider this part, okay, so this is 1, 0. If you consider this branch, okay, it is 1, 0. Here you can see that 1, 0. Okay, this is 1, 0. Okay, this line corresponding to 1, 0. The output is 1, 0. Okay, so if you calculate the Hamming distance with this, so 0, 0, no Hamming distance, 0, 0, 0, no Hamming distance, 1, 1, no Hamming distance. No. So here also we have 0 Hamming distance. So here also 0 and here also 0. So you will get 0 here. Hamming distance. Okay. Get it? Okay. And sorry. Here, if you follow this branch, it is the Hamming distance is 3. I will use red color, okay, otherwise you can't see visibly. Okay, so if you come in through this branch, Hamming distance will be 3, and if you come in through this branch, Hamming distance will be 0. Okay, okay, then next clock cycle. Okay, so you can see that it is 0, 1. Okay, and you can go through this branch. Okay, actually there is no any concern to go through this branch, because we can get very large Hamming distance. Okay, so we can stop the calculation through this branch, Hamming distance calculation. Okay, when you are expert, but I will calculate it here also. Here it is 0, 1, and this is 0, 0. So there are one Hamming distance. So 3 plus 1, you will get 4 if you go through this branch. Okay, because this is 0, 0. Output is 0, 0. And here it is 0, 1. If you are going through this line, okay, if you are going through this line, so you can see that here 0, 1. So this line, no? Yeah, 0, 1 and 1, 1. So you will have one Hamming distance. So here 0 and here 1. So you will get 1 here. Okay. I'm sorry. This Hamming distance also should be calculated. Okay. So from here to here, you can say this is second clock cycle. So this is 1, 0. This is 0, 1, and you have 2 Hamming distance. Okay. So 1, 0, 1 Hamming distance, 0, 1, another Hamming distance. So this has 2 Hamming distance. Okay, so 2 plus 0, here you have 2 Hamming distance if you come through this branch. Okay, and also if you're going through this branch, there is another Hamming distance, no? Okay, because this is 0, 1, no? Okay, so this is 0, 1. Okay, so here 0, 0, and you will get 0 Hamming distance here. Okay, so together you will get 2 here. Okay, correct? Okay, 2 here. Okay, so on you can calculate. Okay, so I will stop this calculation because this is 4 and 5, because we need to get the minimum Hamming distance weight. Okay, so calculating the Hamming distance through this branch we can stop. Okay, we can stop. Okay, now I stop here. Okay, but here I have 3. No, if I go through this, I have 1. No, this should be 1. Yeah, this should be 1. Okay, if I go through this line, because here also we have 1, 1, 0. That means 1 Hamming distance. 1 plus 0, you have 1. Okay, 1 Hamming distance up to. If you come through this branch, it is 1 Hamming distance. If you come through this branch, it is 2 Hamming distance. Okay, and so 0, 1, we can go through this or through this. Okay, because this is much higher now. Okay, this is much higher now. So you can see that it is 0, 1. Okay, 0, 1. And if you go through this, it is also 0, 1. Okay, it is also 0, 1. And it is 0. So here also you will get 2. Okay, if you use this path. Okay, and if you use this path, it will be 1, 1. And you sorry, if you use this path, it will be 1, 0, and you will get 2 Hamming distance. Then you will get 1 plus 2, you will get 3. No, here 3. Okay, so you can see that if you see this, okay, if you see this, if you see the minimum Hamming distance point, okay, so first time it is this point. Okay, I hope you get the idea. Okay, so this is from here to here we get 0. Then again from here to here, again we get 0. Okay, now the minimum value we get from here to here. No, we get 1. Okay, and then with 1, if we go through this, we will get 3. And if we go through this, we will get 2. Then we can go through this line. Okay, so this path you can calculate. Okay, so you can see this part. If you got this part, it is a dash line. No, so input is 1. Okay, now you are decoding. Okay, now you are decoding. Okay, so if you are go through this line, this direction, so this is a dash line, so input will be 1. Okay, and if you are going through this line, okay, if you are going through this line, the input will be 0. No, input will be 0 because this is a thick line. This line is a thick line, so input will be 0. Okay, and you have to go through this line. So what is this line? It is a dash line. Okay, so that means again input is 1. Okay, and also you have to follow this line. That means it is a dash line. Again input will be 1. Okay, so you will get decoding signal as this 1, 0, 1, 1. Did you get this? Okay, I think it is correct. No, yeah, here we have encoded 1, 0, 1, 1, and we have decoded it as 1, 0, 1, 1. Okay, so this is how it's decoding. First, we have encoding it using the trace diagram. Then we have decoded it by calculating the Hamming distance with respect to the received bit. Okay, and find the minimum Hamming distance weight. We follow the path with minimum Hamming distance weight. Likewise, we can calculate. Okay, so what if, so here, let's say you will get, here you will receive 1, 1. Consider this special case. Okay, you will receive 1, 1 here. You will receive 1, 1 here. Okay, and if you calculate the Hamming distance, what happened? If you calculate the Hamming distance, you can see that 1, 1, 0, 0. So you will get 2 here. Okay, so in this path you will get another 2 Hamming distance. So this will be 4. Okay, okay, and if you consider this one, so this will be 0. Okay, and again it will be 0 here. Hamming distance. Sorry, this is 1, 0. No? 1, 0 means it is 1. So you will get 1 here because this is 1, 0. Okay, this is 1, 0 path. So 1, 1, if you get 1, 1, Hamming distance is 1 1, that means 0 1 0 1. Okay, so Hamming distance is 1. Here it is 0 0 plus 1 1, you will get 1. Okay, so if you have 1 1, and if you come to this point, you still prefer to go this way, no? Okay, because from this way we can get the minimum Hamming distance. Okay, 1. Okay, and also here this path also we have to consider. So here 1 1 and here 0 1. So this path is 1 0. So this Hamming distance also will be 1. Okay, so now you have two options. You can go through this path or you can go through this path. Okay, so you can see that if you go through this path, okay, so you will decode the signal as the input signal as 0. Okay, but if you go through this path, okay, you will decode the input signal as 1, no? So this will be you will decode it as 1. Okay, so then you will get the error. Okay, so you can see then, okay, if you select this path, you can directly decode the signal, but if you go through this path, you will get the error. Okay, so that means sometime this method can't correct all the errors, no? This method can't correct all the errors. Okay, sometimes error can be happen, but we can minimize. Okay, we can minimize the errors. Okay, so as exercise, you can after the exam, okay, after the exam as exercise, you can do by changing this value 1 to 0. Okay, by changing this output value and again calculate the path, and you can find the how many bits error and how we can decode correctly. If the received bit is wrong, okay, you can see how many bits we can correct and how many bits we can't correct. Okay, so you can do it as an exercise. Okay, okay, so I hope you get the idea how this convolution code is used to decode and how it used to encode. Okay, so shall we move to the question 6? Okay, so we will just do the question, okay, without discussing much thing, okay, because now it is already past the time. Okay, I'm sorry for that. Okay, so give me a half an hour, I will try to do this. Okay,